So, a very good afternoon to you all. So, I welcome you all to the fourth session of geoprocessing using Python. So, in today's session, we will discuss about raster data processing using Python. So, basically, we will see how do we read different raster data formats using a Python library. So there are actually multiple Python libraries available for this purpose, but specifically we will discuss a library called GDAL, Geo Data Abstraction Library. Then we will see how do we read a raster data using GDAL library. Then we will visualize the data using matplotlib. Then we will see how do we create different types of false color composites for visualization using matplotlib or numpy. So I will start with raster data. So what is raster data first of all? So anyway, in the first lecture you were briefed about raster data. So just for a quick refresher, I will be just telling about raster data. So raster data represents objects or variables on the Earth's surface. So any object or variable on the Earth's surface has a matrix of values. So that object may be the image of the Earth, or it may be temperature of certain area of the Earth, that is represented as a matrix of values in the form of pixels, cells or grids. Okay, any object or variable on the Earth's surface that is represented as a matrix of values in the form of pixels, cells or grids is raster data. So a raster is an image with a matrix of values representing the values of some observed attribute. So raster is an image with matrix of values. So raster is an image with matrix of values. So these values represent some observed attribute, like it may be temperature or a reflectance of the surface, land surface temperature, or any measured value it can be. So a raster image can have multiple bands. So bands of a raster corresponds to different variables. So bands of a raster image may correspond to different variables. All of them usually be of the same matrix structure. So these different bands may represent spatial variability of temperature, elevation, rainfall, etc. over a region. So these bands may represent temporal information or maybe reflectance in different electromagnetic bands, EM bands. So like a raster image can have multiple bands, so can be a single band or multi-band. So when there are multi-bands images, these multi-bands may represent some temporal information like temperature at time t0, t1, t2, t3, or these may be reflectance values in different bands, maybe like red, green, blue, or some other bands. So this is how a raster image looks like. Suppose this is an image of certain area on the Earth. Now suppose if we zoom into this area, then it looks like this. So cell of or grid of pixels or cells. So every pixel represents some value. So internally, if you see, this will look like, or this will be represented as an matrix or a grid of cells with values. So every cell will represent the reflectance in that pixel. So this pixel will correspond to some location on the Earth's surface. So raster. So this is a raster. So raster bands. Some rasters, the raster may be of single band. Some rasters have a single band of data, while others might have multiple bands. Basically, a band is represented by a single matrix of cell values. So a single band is represented by a single matrix of cell values, and a raster with multiple bands contain multiple spatially coincidence matrices of cell values representing the same spatial area. So when we are talking about multiple bands, so all bands will represent multiple spatially coincidence matrices. Means all the bands will represent the same area, but the values on those bands may be like those may be temporally different from each other, or maybe in different electromagnetic band. So an example of single band raster, like suppose if we are going to represent the digital elevation model of certain area, so that will be generally represented using a single band raster. Then each cell in the digital DEM will contains only one value that will be representing the surface elevation at that area or point. So if you see the single band raster, so single band raster can be a binary image, so where the value of every pixel will be either 0 or 1, or it could be a grayscale image. So grayscale image representing different levels of different shades of gray. So maybe suppose if you are representing an image using 8 bits, then it will have 255 different gray levels. And the same thing, like if a single band image can be represented as a color map image as well. So suppose if we have a classified image, where like we have classified image, okay, so like you see that forest areas are represented using 4, or then some area, water is represented using 2, urban is represented using 1, and so on. Suppose if we have a classified image, a classified single band raster image, that can be displayed using a color map also. Actually, though continuous values also can be represented using color, but here like this can be represented as a color. Like then we can say that all cells with value 5 will be represented with blue color, or all cell values with a value 4 will be represented using color green, yellow, and so on. So this way single band raster can be shown as a colored image using a color map. So anyway, we were discussing about actually we can say that a raster can be single band or multi-band. So single band raster may be like when you are representing digital elevation model, so that is represented as a single band, and every cell represents the surface elevation at that point. So similarly, there can be image can be multi-band also, or a satellite image, for example, commonly has multiple bands representing different wavelengths. So every band represents a different wavelength from from ultraviolet through the visible and infrared portion of the electromagnetic spectrum. If you see individual band of the image, maybe red band image may look like this. So this area, and the same area in the green band may look like this, and in blue band it may represent like this. So here we are representing every band as a grayscale image. So when we combine these red, green, and blue, or any other band of combination together, so by combining 3 bands together, then we get a RGB composite, or we can say colored image. So when we combine the 3 bands together, then we make a colored image. So like there, if you see, if we combine these 3 together, we get a colored image. So similarly, like here we have the multi-band raster data set in 3 different bands. When we combine these R, G, and B bands together, we get a colored RGB composite. So like here you can see that this is the list 3 natural color composite of Haridwar area taken by a list 3 sensor of ISRO's Resource-2 spacecraft. So these are the sources from these images, and the contents have been taken. So now after knowing the basics about raster data, let's see how do we read the raster data using Python. So for reading raster data, we will be using a library called GDAL. So GDAL stands for Geospatial Data Abstraction Library. So this is basically a library for reading and writing geospatial data formats. So GDAL supports almost all the available raster as well as vector data. So it can read and write most of the data formats. For few data formats, it just can only either read or write. But in general, GDAL supports almost all the raster and vector data formats. So GDAL is a library for reading and writing raster data. GDAL represents single raster abstract data model and single vector abstract data model to the calling applications for supported data formats. So actually what happens, all the different data formats like GeoTIFF data format may be different from IMG data formats. All the data will be written to the disk depending on the format. So different softwares will or different formats will write the data differently on the disk, but GDAL represents all the data as an abstract data model. So the underlying details of the data, how the data is stored on the disk, is hidden from the user, and GDAL represents an abstract model of data, either vector or raster, independent of the format. So whether you are trying to read a GeoTIFF image or IMG image, or maybe any other like NV format, any format you are trying to read, so just GDAL will represent an abstract data model for that model. So the internal details of the format will be hidden from you, and you will just get an abstract data model. So on that you can apply different operations irrespective of the underlying format used. Plus, apart from this, GDAL also comes with a variety of useful command line utilities for data translation and processing. Suppose if you don't want to write something in Python or something else, then there are certain command line utilities also are available with GDAL. So those command line utilities also you can use for processing your data. So we will be discussing about both. So first we will see that how do we use those command line utilities, some few basic command line utilities, and the same thing we will try to do in Python as well. So like, what are the different advantages of GDAL? Like why should we use GDAL? So first and foremost, GDAL is free and open source. So GDAL is available free of cost, and it's open source as well. So then if you want to change something on GDAL, you can change that as well. So it supports over 80 plus image formats and map projections. So all raster and vector data formats, almost all the data formats are supported by GDAL. So GDAL has command line utilities, plus there are few command line utilities available in GDAL, plus it has APIs for C, C++, Python, R and Java programming languages as well. So like if you are working in C, C++ or Java as well, so for these also GDAL has APIs available. Plus GDAL is used extensively by world's large geospatial data services. World's large geospatial data services like Google Maps or Bing, they also use GDAL. Plus GDAL has extensive test suite and active developer community. So the test suite, there are active test suites and active developer community. So the daily new features to the GDAL are getting added, and the documentation of GDAL also getting improved day by day. Plus they are adding new features. Moreover, GDAL also includes extensive support for vector datasets as well. So this is a complete package. So either vector, raster or any format, you can use GDAL for processing the data. So as we discussed that, irrespective of the underlying data format, maybe GeoTIFF, IMG or NV format, so GDAL represents an abstract data model to the user. So a dataset represented by GDAL dataset is an assembly of related raster bands and some information common to them all. So irrespective of the data format used, so the entire data format will be represented as a dataset. So the dataset will be the assembly of all related raster bands in the image and the metadata associated with those information combined into a single unit. So when you see an image, so when you read an image using GDAL, you will see that as a dataset. So dataset will have multiple bands and some metadata associated with that data. So a dataset has a concept of raster size, like any raster image will have size. So like in pixel and lines. So how many pixels are there and how many lines are there. So a dataset is also responsible for georeferencing transforms and coordinate system definition of all the bands. So these all information together, like projection information, transformation information, different data bands. So GDAL will represent an abstract or uniform view of all the data, so respective of the format as a data set. So a data set itself can also have associated metadata or a list of name value pairs in the form of string. So this is an example, like irrespective of the underlying format, when you read an image using GDAL, it will be represented as a data set. So the data set might contain one or multiple bands plus geotransform and projection information associated with that image. Plus a band in turn may have a data array, so data array containing the data of that band and some overviews at reduced resolution for faster display on the screen. So if your image is suppose if you assume that if the image is very large and if you are drawing it on the screen, then it takes lot of time. So and if you are looking at if you are zooming out the image, so while you zoom out the image, so the overviews of that image will be rendered on the screen instead of pixels at the native resolution. So this way image will be rendered faster on the screen. So just in a nutshell, so whatever image you are going to reach, irrespective of the format, will be represented as a data set. So data set will contain one or multiple bands plus geotransform and projection information. A band in turn will have data array and there may be some overviews at reduced resolution on that band. So this is the raster data model of JIDAL. So now let's discuss about map projection just quickly. So a map projection is a way to flatten a Earth surface into a plane. So if you see, the Earth surface is three-dimensional. So when we are going to project into a map, so we need to convert it to a two-dimensional surface by using some mathematical transformations. So converting a 3D surface to a 2D surface requires some systematic transformations of the latitudes and longitudes of location from the surface of globe into the location on a plane. So the projection is converting a 3D surface to a two-dimensional surface. So all the projection of a sphere on a plane necessarily will distort the surface in some or other ways. So like these are the different projections. Then with every projection system, there will be a coordinate system also, so that with reference to that coordinate system, we can tell the location on that plane. So there are numerous conventions used globally for representing the coordinate system for the map data. So dataset coordinate systems are represented as OGIS WKT strings. So this WKT, this string can contain like overall coordinate system's name, like what is the name of the coordinate system, like if it is attached to some geo coordinate system, the name of that geographic coordinate system, datum identifier, ellipsoid name, semi-major axis or an inverse flattening, prime meridian name, offset from the Greenwich projection method, type, list of projection parameters, units name, and name of and ordering of the axis like first latitude or longitude and so on. So the projection system can be coordinate system and projection system can be represented in different formats like PROJ4 or OGC-WKT, or there can have directly short EPSG codes as well, or it can be represented in an XML format as well. So this way an coordinate system can be represented. Now coordinates of an image, if you talk about an image in an image coordinate system, so any pixel in the image will be represented as pixel number and line number. So if you go in the Y direction, that is called lines, and in the X direction it is called pixels. So if you take actually in the image, this top left corner will be 0 0, and this direction are lines. This is first line, second line, third line, and this is pixels, first pixel, second pixel and fourth pixel. This way in image coordinate system a pixel is referred using pixel number and line number. So suppose if you are referring to this last pixel, here we can show if there are n pixels in the line, so n pixel comma line number 0. So similar, this will be n pixel number of pixel comma number of line. This pixel will be represented by this coordinate. So line number and pixel number. Now actually what happens, this is an image coordinate system. Now when we are referring to an image, so we need to refer to its real world coordinates, like this pixel represents what latitude and longitude on the Earth surface. So we need to convert from the image coordinate system to the real world coordinates. For that a geotransform information is utilized. So a geotransform is an affine transformation from image coordinate or pixel line to the geographic coordinate space, like projected or geographic coordinate. So this way we will see that how do we convert from the image coordinate system to its real world coordinates by using geotransform information. So actually with the help of geotransformation. So a geotransform consists actually a set of 6 coefficients. So these are 6 affine transformation coefficients. With the help of these, see, with every image, these affine geotransforms will be stored. So with the help of these affine transformations, we can convert an image from real world coordinates to the from the image coordinate system to the latitude, longitude or geographic coordinate system. So it will contains the 6 elements, like GT0 coordinates x coordinate of the upper left corner of the pixel. Then GT1 is the east-west resolution, or what you say pixel width. Then GT2 is the row rotation, like typically 0 if the image is north up. If image is not at all rotated, then this number will be 0. Then y coordinate, then rotation in y direction, then the north-south pixel resolution. So these 6 elements represent this. So with the help of these, we can convert from real world coordinates to the to the real world coordinates from the image coordinate system. Like suppose this x0 is the 0, and if resolution is 4 in x direction and 3 in y direction. So this, like this, if you can be converted x0 plus 4 px and y can be y0 minus 3 py. So this way we can convert by applying this formula. You can convert this. So like this is the simple formula for that, same thing only. So in case of north up image, these will be, the coefficients will be 0, and this, and we will discuss, we will see with an example as well last. So now let us see these all in action. How do we do it? So for this, actually I have some I have an image list 3 image acquired by list 3 sensor of resource set 2 satellite. So I have just stored them in my this particular directory, D drive NNRMS and Nainital. So first I am changing my working directory to this import OS, and I am just changing my directory to the my working directory to the directory where my data is available. So just now first thing I will show you a command line utility for extracting information about this particular raster. Now I have an image called nainital.tif. So first command, like if you are preceding any command in Jupyter notebook with exclamatory mark, it means it is a system command. So actually when you install JDAL, so actually I did not talk about installation of JDAL. So JDAL, anyway, you can activate your environment and you can just install this conda install. So there are multiple channels from which JDAL is available. Either you can download it from Conda Forge, and you can just say JDAL, or you can see download from Anaconda channel as well, JDAL. So JDAL is available from multiple ones, quite easy. So once JDAL is installed, you need to just this JDAL. These all utilities also gets installed automatically with the JDAL. So JDAL info is one command line utility. So for starting the command line utility, command is, so this you need to proceed with an JDAL info. JDAL info minus, actually we are giving a option like switch for no MD. No MD means don't print metadata. Then the name of the file for which you want to extract information. So if I run this JDAL info no metadata, now you can see that this JDAL info runs this, gives this output. So if you just quickly read about this, so it says that driver geotip. So because the format of the file is geotip, so it says geotip driver. Then files are nainital.tif and nainital.tif.ox or .xml, some associated file with this. Then the size of this image is 1151 by 1151. Then the coordinate system associated with this image, like this is the projection information, GeoGCRS WGS84, and this is the information about this GCS. And these are the origin pixel. These are the coordinates of the 00th pixel of the top left. Then this is the pixel size. In x direction, this is the resolution 0.002 degree, and in y direction minus 0.002 degree. Then these are the coordinates of the different corners. These are the coordinates of upper left corner, lower left, upper right, and this all. Then this is the band information. So there are 4 bands in this. This is a 4-band raster image. So the image is stored as in the blocks of 1151 by 1151 size, and the data type of each pixel is unsigned 16-bit integer, and the color interpretation, you can say that anyway we have not set the color interpretation of with the image, so it says adds gray, and This is the minimum pixel value, like 49 for in this band 1. Minimum pixel value is, minimum pixel intensity is 49 and maximum is 436, and like this these are mean, standard deviation. This way this is the information of the all bands. So this way you quickly, by using GDAL info, you can get the information about your raster image. Now let us see how do we get the same information using GDAL using Python. Okay, so once you install GDAL, so GDAL comes with a name, package name called OSGeo. So from OSGeo, because as we explained that all the functionality of the Python doesn't get automatically loaded into the interpreter by default, so we need to import additional functionality. So OSGeo is the name of the package. So from OSGeo, first thing you need to import GDAL. So anyway, I have imported from OSGeo GDAL. Then I am using other libraries like matplotlib. So matplotlib we will be using for plotting the image. Then numpy, if required, we will use. And then import and OSGeo, OSR. Okay, these maybe we will discuss later. So as of now, only the important library is GDAL. So OSGeo is the name of package and GDAL is the library, or what you call function or class available. Actually, it is class. From OSGeo import GDAL, and then these are the required libraries. Then I am just saying that okay, this is anyway I am in this directory only. This is, I am changing my working directory to the directory where my data is available. So now next I am defining a variable called file name. In that I am just storing the name of file. So if I am not changing my working directory, I need to give the complete path. Anyway, now I have changed my working directory to the directory where the data is available. So I have just given the variable name nainital.tif. So now next thing comes, how do we open the file? For opening the file in GDAL, we need to call the function GDAL.open. Actually, you should be careful because Python being a case-sensitive programming language, so GDAL.open may be different from GDAL.open. So GDAL.capital O, GDAL.open. Then you need to pass it the name of file which you want to open. So here we have stored the name of file to be opened in the variable file name. So if I run this GDAL, and if next I am printing this ds, so it says that osgeo.gdal.dataset. As I explained that irrespective of the underlying format, the GDAL will represent the image as a dataset. So dataset will have multiple bands plus other information, associated information. So this is GDAL. Now suppose if there is an, actually GDAL doesn't represent any. Suppose this, if I change the name of this file nainital.tif, now if I run this, it doesn't do anything. So it has returned none. So it is better always, like you check for, like if ds is equal to none, you just print some information. Otherwise you have to enable the exception handling in GDAL. Anyway, by default it is disabled. So for better, you always check that what the GDAL.open has returned. If it has returned none, means it could not read your file. Maybe your file was not available or the format was not supported. So it is better practice. You always check what ds has returned. So anyway, here you can see that it has returned a data set. It means it has read, it was able to read the file correctly. So now let us see in the GDAL info, we saw that first thing it was returning names of file. So same thing like from the data set, if you want to get, so you can call this function ds.getFileList. So ds.getFileList returns the files associated with this particular image. So it says that nainital.tif and nainital.tif.aux.xml, the same output which we were getting here. So with this also we are getting geotif, nainital.tif and this tif.xml. So we'll not spend much time here. So then similar way, suppose if you want to extract the pixel or image size in x or width of your image, so it says 1151. So if the method is ds, your data set, whatever you have assigned GDAL.open, ds.raster x size. Similarly, for getting the information in height of the image, ds.raster y size. So it gives you, because the image was 1151 by 1151. This way you get the size of image in x as well as y direction. Now suppose if you want to extract the projection information associated with your image, then you can call the function ds.getProjection. So ds.getProjection returns you the projection information of your associated with your image. So if you see, this is the coordinate system with GeoGCS. So the image is in geographic coordinate system, and this is the details of that GCS system. Similarly, now suppose if you want to extract the geo transformation information associated with the image, so then you can call this function. Anyway, it is like with the help of this is ds.get geo transform. So just you need not remember all these full math function names. Just with the auto completer gives you the hint. So this gives the geo transformation information, like this is the coordinates of x, this is longitude of x0, then is the pixel resolution in x direction, then this is 0 means the image is north up, image is not at all rotated. Then this is the latitude of top left pixel, and this is rotation is 0 means the image is directly north up, no rotation in the image. This is the resolution in y direction. If you see the resolution in y direction is negative because we are going from the top to bottom. Now this way, same way like origin pixel size, if you want to this. Now suppose you know the pixel number and line number. From this, suppose if you want to calculate the real world coordinates of your pixel. So for that in GDAL there is a function available, GDAL.apply geotransform. So GDAL.apply geotransform will convert from image coordinate to the real world coordinate or latitude longitude. So GDAL.apply geotransform takes 3 arguments or first is the geotransformation information, this affine transformation array, then pixel number and line number. So suppose this upper left corner will have pixel number and line number to be 0 0, and the upper right corner will be ds dot in like width of our image, and y will be 0. Similarly, lower left corner will have x will be 0 and y will be equal to the height of image. Similarly for all coordinates, and the center will be half. So this way you can convert the corner from line pixel to the real world coordinates by using GDAL.apply geotransform. This way you can see that it could calculate the coordinates of these corners. So these will be matching with these numbers shown here. So this way, by applying, so you need not do those calculations manually. You can just apply GDAL.apply geotransform and convert from pixel coordinate system to the real world coordinate systems. Then suppose if you want to extract the metadata, associated metadata from the image, then you can just call this ds.get metadata. So with this you will get whatever metadata is stored with the data set. So here it is shown that metadata area or point, it is area. So what does it mean? That the pixel represents the average value in the area. So it may be point also. So if it is represented as a point, it means the pixel represents a point. But right now in the metadata it is stored as this pixel represents an area. So this is the average pixel of that particular area. So here the pixel represents an area, not a particular point. So there is another package in Python that is called petty printing. So pprint prints the metadata in quite good readable format. Actually this is small information, so it is showing that we will see that when a large metadata we are printing, it prints a good in good readable format. So similarly, like image structure, like it says that it is interleaved, pixel wise interleaved. Then suppose if you want to extract like how many bands are there in your image, you can just call ds.raster count. It represents the number of bands available in the image. So similarly, now suppose we want to extract other information from the image, and like we want to loop over all the bands of image one by one. So for that, what we need to do? We need to loop over all the bands one by one. So in our image there are 4 bands. So we are actually in the GDAL bands. Generally in the computer science, band indexing starts with 0. But in case of GDAL, the bands start from 1. So if there are 4 bands in the image, then band 1, band 2, band 3, 4, band 4, not band 0, band 1, band 2, band 3. So for this, because of this reason only, we are starting a loop for I in range 1 to number of ds.raster count. So ds.raster count represents how many bands are there plus 1. So we want to go from, because we want to loop over from 1 to 4. Now suppose if you want to fetch some particular band from the image, so then you need to, as I explained, the data set in turn contains multiple bands. So you need to call this function dataset dot get raster band and pass it the argument band number, which band you want to fetch. So ds dot get raster band, like 1 if I am passing, it will fetch the band 1. Then on this band you can get like what is the get color interpretation, then you can get block size and overview if there is any overview associated with this band, and if there are multiple overviews then you can loop over these overviews as well. So this way we are iterating over all the bands one by one and getting the information of that band as it was retrieved by GDAL info. So here we can see that information. So anyway, this same information whatever we were getting with GDAL info you get. So once this is done, we can just delete this data set. So now suppose if you want to get actually same thing, like instead of GDAL utility you can call this as well GDAL.info, like info. So I say nainital.tif. The same information you can get by this as well, GDAL.info. Instead of calling the command line utility there, GDAL.info also you can call. So now suppose if you want to calculate the statistics, so then you can call to GDAL info, you can pass another argument called minus stats. So it calculates statistics of the image, like band 1 this is the minimum value, band 2 this is the minimum value, and so on. Like if I see this, so here you can see that anyway by default also it was computing all those things. So these are the basic statistics about your image, like minimum value, maximum value, standard deviation and mean of the pixels. Now suppose same thing if you want to calculate the statistics using Python, just you can same thing, like you can open the with GDAL.open file name, then you can iterate over all the bands one by one, and like you can fetch the particular band by calling band.get raster band ni or like band number. Then you can call, and on that band you can call this compute statistics, band.compute statistics, and it takes one argument either true or false. That says that if you are passing it false, so it means that the statistics will be computed on the actual image. So but now suppose if you are passing it true, then it will be calculated on those overviews, so you may not get the exact statistics. So suppose if you want to calculate the statistics on the native image, so then you need to pass it false. So like this we can iterate over all the bands one by one and calculate these values. So this compute statistics returns min, max, mean and standard deviation. So this way you can calculate the statistics of your image by using just a single command. Now till now we have just talked about like data calculating statistics. Now let us visualize the image, how the image what we have read looks like. First of all, let us see, first we will try to visualize a single band of that image. Now because our image was having 4 bands, so now let's from the data set fetch band 1 from our data set. So for that the function available is like our ds. In ds we have stored, ds is our GDAL.open and file name. Now if I call ds.get raster band and I am passing it band 1, so I am fetching the band 1 from the image. So band, now it has returned me a band. Now from this band, because if you remember this slide, so a band will contain data and some overviews. Now actually now we are not interested in overview, so we want to just see the data. How does that data look like? Because it will be a matrix or it will be a 2-dimensional array. So now let us see how does that data look like. So now for reading the data from the band, we need to call this function band.read as array. So it will return a data. Now suppose if I print this data, so this is a 2-dimensional matrix, right? Like if I see the data dot shape, so it says 1151 by 1151. So actually NumPy for the performance reasons, it doesn't print the entire array. So just initial some elements of the array are printed, like these are missed, and similarly on the rows. So if you want to see all the data together, then some settings are there in the NumPy that you need to see. With that you will see the entire array. So just for performance reason, it just clips all things and shows only overview of that data. So this way we can see that this is the data. Now let us see how does this matrix looks like. If suppose if you plot it on an like how does it visually looks like. So for that, as we anyway I explained in the morning session, for plotting a two-dimensional array or image, we need to call the function IMShow, right? So for anyway we are not using here explicitly creating figure and axis, and on that we are not plotting. We are just directly using pyplot because here pyplot is more convenient. So first of all, I am creating a figure of size 10 by 10. So plt.figure 10 by 10. Then next I am calling plt.imshow function. So plt.imshow, and here I am passing the data array which I band 1. So if I run this piece of the code, so you see the image. So the contrast of the image may not be good because anyway, so later on we will see how to improve this contrast. So here you can see that this is the band 1 of our image, like whatever array we were seeing here. Now this is, if you see it visually, it looks like this. Similar way, suppose if you want to plot all the bands of image together, like in multiple plots in an image, so same thing, like you can iterate over all these bands using this loop, and you can create plt dot, and on the subplots you can keep on adding one by one these bands. So here you can see that all these see here band will be I. So this way, this you can see that all 4 bands together. So this is band 1 image, band 2 image, band 3 and band 4. These are we are visualizing all these bands separately. So later on we can see that we'll see how do we visualize these bands all together, like how do we visualize a RGB composite. So this is all different bands. Once this is done, we need to call this plt.close and free the resources. Now how do we visualize multi-band rasters? Though there are many possible combinations of wavelengths bands, so a typically remote sensing satellite will be observing Earth in multiple wavelengths or different bands. The Earth observatory so generally we will typically select combinations based on event or feature we want to illustrate. You must have learned in the first lecture like what is standard false color composite. So this way we select different combination of bands for visualization. Like for instance, floods. Suppose if you are interested in looking floods are best viewed in the SWS SWIR band, SWIR NIR and green light, because muddy water blends with the brown land in natural color image. So in natural color image you will not be able to differentiate between muddy water and brown land. So for that, if you visualize the image in SWIR NIR and green band together. Similarly, there are different combination of bands for making the standard false color composite. Like suppose if our satellite is collecting images in 4 or 5 bands, but for visualization we can select any of these bands for R, G or B. Like here we have selected band 3 for blue, band 4 for green, band 5 for red, and we make a color composite. So this is called a false color composite. So similarly we can select any combination of these bands. So like this band 1 can go to blue, band 4 can go to green, band 5 can go to red, and then we can make a color composite. So this is called false color composite. So these false color composites are created because some features may not be, some features will be visible in different combination of band properly. So for visualizing those features we make different false color composites. So let us see how do we create, because this image is list 3 image. So these are the bands of list 3. List 3 has these bands, and we will see how do we will combine these color composites. So these are some standard false color composites. like near infrared is represented as red, green as blue, and red as green. So this is a traditional band combination useful in saying, so when if you are interested in seeing the changes in plants health, then you can use these combination. NIR you can use as red, green as blue, and red as green, or like these are combinations. So if you are interested in seeing the floods, you can SWIR band you can use as red, NIR as green as blue, and like these are some different combinations. Generally, thermal infrared is usually shown in the tones of gray to illustrate some temperature. So this is one of the standard false color composite where near infrared is shown as is represented in red and green in blue and red in green. So let us see these images. So this our image was a list 3 image. So like here I am now by default if we see, so if we see the list 3 image, so in the list 3 image the bands available are in the list 3 is band 1 is green, band 2 is red, band 3 is NIR, and band 4 is SWIR. Now if you see band 1, so there is no blue band, so green, red, NIR, and SWIR. Now from this, suppose if you want to make a standard false color composite where in red we want to store NIR, and in blue we want to store green, and in red we want to store for and the red we want to store in the green color. So for that, now I am using the function like band dot read as array. So band dot read as array, if you don't pass any argument to band dot read as array, then it in that case it reads all bands from the image. But now suppose now because I am just interested in reading any 3 bands, so for that in that case I can pass an argument to the read as array function, a band list argument. So band list, this will be an array in which all bands I want to read. Suppose in here I want to read band number 3, band 2, and band 1. So this way I can see, I can just read only 3 bands. So I think this version of JDAL is not supporting this. So if it doesn't do this, we can do it like this. So actually I think this the version of JDAL available here is a bit old. Then anyway, let us see this ds.read as array. Now if I see the data of sheet, so this by default it has read all the 4 bands, but as of now we are interested just only in 3 bands, right? So now we will from this 4 we will just take 3 out, 3 bands only. So I will say so three combinations. Actually when matplotlib this data shape, if you will see, this is like so this data is available in, so not this, I want 3 comma all rows comma all columns. So for Oh, sorry, this is, I am referring to the different multi-data. So now, because I was interested only in fetching 3 bands, so if you see the shape of this data, it says 3. So this is in the form like channels and height comma width. But actually when we plot a multi-dimensional array using matplotlib, actually it requires the data in the form of height, width and channels should come at last. So for transforming this data to that format, we need to call the function called np.transpose. So what np.transpose does, actually np.transpose permutates the access of the data. So here we are swapping the access of data, like axis 1, in the 0th axis we are getting 1 and second axis 1 and 0. So this channel number we are shifting to the last. Like here if I see multi-data, then if you see the shape of the data, it is now, see, initially the shape of data was like 3 into 115 into 1151. Now it is in the shape 1151 into 151 into 3. So now suppose if I visualize this, so this way you can see that we have visualized a multi-band raster. So this way, by changing these datas, you can change, like suppose if you want now instead of this we can say that 1 to 4. Similarly, actually this band list argument, because this is looks like a bit older version of GDAL. So now I can say, now if I want to represent different, like say 1 to 4, and here I have created a different false color composite by use. So this way you can make different color combinations. Actually this the latest versions of the GDAL take this band list as an argument. So there you can pass different there you can pass different band combinations, and like suppose if you want to read the band 233 and so on, then because this is not working here, this way you can create different multicolor standard false color composites using GDAL and visualize them using matplotlib. So similarly, now suppose let's see how do we read raster block wise. So rasters are generally made of blocks. So blocks correspond to the rectangular subpart of the raster. So first value is the width of the block and second is the height of the block. Now suppose if your image, the size of your image is very large and the memory available at your system is not so huge. So what you can do, you can read the data partially block by block and then do the processing on that image, save that image. So this way you can process a huge image by reading block wise. So like this was your image, and suppose assume that this was the block size in block size of image. So in this block size you can slide over these blocks. So once read this block, this block, this block, and go to the last. Similar way you can go to the up direction and read on this way. So this is the same way, like we have opened the file get raster band, then we are calculating the size in x direction and y direction and getting the block size, and with this loop we can iterate over these all blocks one by one and read the image. So this is quite simple. This way you can read the image block wise. Now let us see how do we read. So this was HDF file. Now this was a DOT file. Same way you can read IMG or some other format. Now let us see how do we read an HDF file using Python. This is the morning some student asked this. So hierarchical data format is a set of file formats, maybe HDF4 or 5, designed to store and organize large amount of scientific data. So many of the data you get in HDF format. So let us see how do we read this using Python. So if you see the data model of HDF, so HDF also If you read HDF also is represented using a data set. But what happens in case of HDF, inside a data set there will be some other sub data sets. So inside the sub data set, a sub data set can contain multiple bands and the geotransformation information associated with that band. So while reading a HDF data set, you need to first open that data set, and inside that you get all these sub data set, and you need to read those sub data sets one by one. So let us see with an example. So here I have a HDF file. So this is a mod 11A1 data available. So this is the name of the file. So first thing is same as what we have done previously. So you need to just call gdal.open and pass it the name of file which you want to read. gdal.open HDF file. Now if I see this DS, if I print this is showed that it has read a data set. It means my file was read successfully. Now this is a HDF file. So I know that this must contain some sub data sets. So for first I need to extract the sub data set. Now I cannot directly access the bands. I need to first extract those sub data sets. So for that I need to call this function ds.get sub data sets. So if I call this SDS, now this has returned and I have stored them in a SDS. Now if I type SDS, SDS is a type of list. So this has, because in HDF can contain multiple sub data set, like suppose if I reading MODIS file, so it may have daytime land surface temperature, nighttime land surface temperature, viewing angle. So all these bands will be represented as different sub data sets. So now suppose if I want to look into this, so I can iterate over this SDS. So this is a list type. So for SD, so in this SDS there will be that SD, actual SD, and the description of that SD. So if I loop over this SDS, it says these are the different sub data sets available inside my file. So like this is the name of the sub data set, and this is the description of that sub data set. If I see, so first sub data set represents MODIS daily 1 kilometer LST, then MODIS 1 km LST QC, then view time, view angle, night time. So these are the various sub data sets available under this data set. So now suppose if I am interested in opening any of this sub data set, right? Suppose if I am interested in opening this MODIS daily 1 kilometer LST. So for this, what I will do is, like suppose if I print this SDS0. So SDS0 is a tuple. So SDS0 is a tuple. First is describing the data set name, and second is the description of this. Now for opening this data set, sub data set, again I need to call this gdal.open function, gdal.open. Then from this SDS, suppose if I want to open 00th, suppose I want to read the day LST. So I need to pass it SDS 0, 0. Now instead of this, suppose if I want to read this MODIS grid daily 1 kilometer LST view time. So then I need to pass SDS, like this is 0, 1, 2. So it will be SDS 2, 0, because 0 is in that element. So it's like this way, because this 0 will remain always 0 only, and this number will change according to the which sub data set we want to read. Now if I see, this is again a data set type. From this I can extract the projection information. Then it can have some bands also, like I said, data.get raster count. Data.raster count. So it says this is a single band only. So now suppose if I want to fetch the data, so on the data I will first fetch that band, and on that I will call this read as array function. So maybe LST day or night, whatever it is, data.get raster band read as array. Now this is, I think, with the scale factor. If you see the metadata, it will show you that this has some metadata also. Now this, if you want to convert it to degree centigrade, this we need to multiply it by this multiplication factor and offset of minus 273. So we are doing this. Now suppose if we plot this way, you can see that we have read this, and this is temperature. This may be temperature in Kelvins. So this way now suppose in LST day we have read LST 1 is QC actually, then we need to read LST 0. So this is the land surface temperature. So similar way now suppose if you want to read this emissivity, so then this will be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 8. So I will pass it here 8, and then emissivity values I can get. So this way we can read an HDF file using this GDAL. Actually there are other libraries available. If you don't want to use this GDAL, there are like XArray also you can use for reading these files. Now suppose if you want to see this metadata, so for this now you will see how the pprint uses. So now directly ts.get metadata, so it prints this metadata in a nice readable format. Suppose if I am going to print it like normally using print, just print, you will see the difference between this. Like if I say print get, so here it prints like this. So this is not nicely formatted for reading. So if you print it using pprint, it prints quite in nice way so that it can be read quite easily. So you can write compact equal to true. This way you can use pprint for printing the metadata nicely. So here it says emissivity into scale factor plus offset, and then scale factor they have given somewhere. So this way you can read an HDF data. So thank you very much for today.